will find out the potential energy, kinetic energy and total energy of a particle when performing the simple harmonic motion at point A. Now we want to see again these three values at different position. First position is main position. What we get there? First one, that is case 1 at main position. That is at point O. What we get there? At point O, the value of x which is equal to the 0. If we substitute this value, that is x which is equal to 0 in 2, in 3 and in 4, so what we get here? Suppose that if we substitute the value of x in 0, so what we get here? Kinetic energy which is equal to the what we get here? Half of k into the a square minus x square, but the value of x is 0. So what we get here? Half of k into the a square minus 0 square. 0 square is nothing but the 0. So what we get there? Kinetic energy which is equal to the half of k into the a square. So this will be the value of kinetic energy at main position. Similarly, we want to find out the potential energy. What we get there? Potential energy which is equal to the what we get there formula is half of k into the x square, but the value of x is 0. So what we get there? This 0 square is also 0. So this value of this potential energy is 0. Right? So this is the potential energy at main position. Similarly, the value of total energy is what we get there. Therefore, total energy which is equal to what we get there? Kinetic energy plus potential energy. At main position, the value of kinetic energy is half of k a square, and the value of potential energy is 0. So what we get there? Total energy which is equal to the half of k a square. Right? So this will be the kinetic energy, potential energy and total energy of a particle at main position. Similarly, at extreme position, that is at A or B position, what we get there? At that position, what we get there? The value of x which is equal to the plus minus of A. Right? Now here we want to substitute these values in the equation of kinetic energy, in the equation of potential energy and the equation of total energy. So what we get there? See here. Kinetic energy. We know the formula of kinetic energy. Half of what we get there? K into the a square minus x square. But the value of x is plus minus of a, and we want to take the square of that. We know that the square of whether positive value or negative. What we get there? Simply we get the positive value. So that's why here what we get there? A square. So a square minus a square is 0. So that's why the value of kinetic energy at extreme position is 0. Right? Similarly, potential energy. Now, potential energy. What we get there? Potential energy. Formula of potential energy is half of k into the x square, but the value of x is plus minus of a, and the square of plus minus what we get is simply plus. So what we get here? A square. Right? So this will be the value of potential energy at extreme position. Now total energy. What we get there? Total energy which is equal to the kinetic energy plus potential energy. Here the value of kinetic energy is 0 and the value of potential energy is half of k into the a square. So finally what we get there? Total energy which is equal to the half of k into the a square. Right? Here, suppose that if we give the numbers to this equation, so what we get there? Suppose this will be equation number 4, this will be equation number 5, and now this will be the equation number 6. See here, equation 4 represents the total energy at point P. Here equation 5 represents the total energy at point O, and equation 6 represents the total energy at position A and B, that is at extreme position. Right? If we see the equation 4, 5, 6, then the value of total energy is remain same. Right? From equation 4, 5 and 6, the value of total energy of a particle is half of k into the a square. It means that total energy is remain same, and if the total energy is remain same, then such quantity called as the conserved quantity. Conserved means that total energy is remain same at all the position in linear SHM. It means that this equation number 4, 5, 6 represents the conservation of a energy of a particle in linear SHM. Right? So this is about the total energy. Now we want to see the graphical representation of this total. Two horizontal lines. This is the first one, and now this is the second one. Here, this lower line represents the position of a particle. Suppose there, if we consider this to the mean position, that is x, which is equal to the 0. This will be the extreme position, that is x, which is equal to the plus a. And now this will be the x, which is equal to the minus a. Right? Then what happened here? Right? And now this will be the upper line represents the value of total energy. So this will be the total energy. What happened? If we see the equation 4, 5, 6, right? In that, at mean position, the value of kinetic energy and potential energy is what we get there. What we get there? At mean position, which value is greater? That is their kinetic energy is maximum. It means that here. And the value of kinetic energy at extreme positions are minimum. Right? So if we join this one, then this will be the curve of kinetic energy. The value of kinetic energy is maximum at mean position and minimum at extreme position. So that's why this will be the curve of kinetic energy. Similarly, the curve of potential energies. What we get there? At mean position, the value of potential energy is minimum, and at extreme position, the value of potential energy is maximum. If we join these points, then what we get there? This will be the nature of the curve. Right? And now this curve represents the curve of potential energy. At extreme position, what happened? Kinetic energy minimum, but potential energy is maximum. At mean position, what happened? Potential energy minimum, but kinetic energy is maximum. Similarly here also. And at these 2 points, here and here also, what happened? The value of kinetic and potential energy is same. Right? So from this one, it is clear that the value of total energy at any position is remains same. So that's why this graph represents the conservation of energy of a particle in linear SHM. Right? So this is about the graphical representation of energy when particle performing the simple harmonic motion. See these equations and graph. Okay.